Good evening. I'll be speaking about the Xcite helicopter-borne time domain electromagnetic system. Xcite was designed by New Resolution Geophysics based in South Africa, and since August 2022 it has been available in Canada exclusively through AXIOM Exploration Group. For this presentation, I will give a brief introduction and talk about AXIOM's airborne data acquisition capabilities. I'll talk about the Xcite system description with some review of some technical specifications. I'll review a case history for a magmatic nickel-copper deposit. I'll review a second case history for a vein-hosted copper-silver target. I'll review a study that was done in Australia from an AEM calibration range that's sort of an objective comparison of airborne electromagnetic systems. I'll do a brief summary, and hopefully at the end we'll have time for some questions. So AXIOM's Geophysics and Remote Sensing Department has been co-collecting airborne survey data for several years. Our helicopter-borne LiDAR survey, co-collected with our GEM systems triaxial gradiometer, was a first-to-market configuration in Canada. And configurations of co-collection options for our helicopter systems include, obviously, LiDAR and triaxial gradient mag, also collected with Radiometrics, and as of the summer, we can collect LiDAR along with time domain EM with the Xcite platform, with total field magnetics, which we collect on the bird, and we measure during the off time, and also with Radiometrics. So for the system itself, it's made of commercial grade PVC, and it is a fully inflatable frame. So the whole loop and the cross beams and the interior loop are all inflatable PVC. And because of this, it is actually quite light. It comes in at about 450 kilograms. It packs in 3 small boxes, about 2 by 2 by 1 meter cubed. This makes it very easy for shipping. The setup time takes about half a day. It's a concentric EM loop, so the transmitter and receiver are in the same plane, so we suspend the bird about 30 meters below the helicopter, and we aim for a 30-meter nominal terrain clearance when surveying. For the transmitter, the loop itself is 18.4 meters in diameter, and it consists of 4 loop turns. And if you look at the image on the bottom, you can sort of see flaps going around the perimeter. These are Velcro straps, so the loop gets Velcroed in place quite tightly. And the way the loop goes around it, the 4 turns are sort of on top of each other. And we have rubber spacings that are put in place between the turns, so the loop doesn't actually touch itself, so we're able to minimize induction noise. We have a single turn bucking coil around the receiver, and we're able to transmit up to 350 amps, which allows us to get a peak dipole moment of about 372,000 amp meters squared. We have a selectable base frequency from 12.5, 15, 25, or 30 hertz. And the transmitted pulse is an approximate square wave with an on time of 4 milliseconds. Onto the receiver. This is a 2-component DBDT system. The Z coil consists of 100 turns and has a 78.5 square meter effective area. The X coil has 200 turns and a 26 square meter effective area. The receiver gates are fully adjustable and extracted from the stream data. And typically we offer 50 gates extracted from 6 microseconds to around 11 milliseconds. We also compute an estimated B field from integrating the DBDT data. So for the waveform description, if you look at the image on the bottom, you can see the transmitter coil sort of strapped in place there, as I mentioned on the previous slides. And also, as mentioned previously, we can see the approximate square wave from the image on the right. Note that The turnoff time is quite fast at 350 microseconds. So this allows us to take readings closer to the actual turnoff event and measure higher anomaly amplitudes. The graph on the right contains two plots, transmitted pulses essentially. So you're looking at current versus time. But they were both taken from a calibration test. The first pulse, the black one, is the transmitted waveform derived from a ground loop. So what we did was we installed a ground loop, flew over it at survey speed, about 40-45 knots, with the bird transmitting, and the induced voltage in that loop was used to derive the transmitted waveform. The second wave, the blue one, was measured directly from the transmitter itself from an altitude of about 1,200 meters, and again at survey height, or survey speed, sorry, of 40-45 knots. And the point of comparing these two responses is to assess our confidence, to calibrate the system and to assess our confidence in measuring the transmitted waveform. And as you can see, there's a high degree of correlation between the two. This is a time lapse of the initial steps of the system assembly. So the counter to the left is going at about 1 minute a second. So as I mentioned, this is a PVC, commercial grade PVC material, which needs to be inflated. So if we do the initial inflation, it doesn't inflate entirely by itself. It's actually compartmentalized, and we inflate each compartment individually using an air pump. We probably pump it up to maybe 80% of its final pressure, but that gives us enough structure to install the transmitter loop, install the receiver, the bucking coil, connect the electronics, and install the ropes. Once all this is finished, we go back and pump everything up again with an air compressor that inflates it to its final pressure, which is really quite rigid. It's very impressive. So that whole install took about 40 minutes. This slide shows a clip of the bird in survey mode, just at a point still in Saskatchewan. So you can see that it maintains its structure quite well. It's quite rigid and has very stable flight operations. All right, case studies. So the first case study is a magmatic nickel copper deposit in Botswana, on the far east of the country near the South African border. These data are courtesy of African Nickel Limited, and the data were compiled from GRS Consulting in South Africa. So this is African Nickel's Sunnyside deposit. You can see here the image, and it's comparable to, it's considered a Selelebe Piquet type deposit, which means it is a mafic magma intruded into igneous and metamorphic hosts. And the nickel and copper were deposited largely along the contact of the sill and the host rock. This is an ore body modeled from drill results. The cutoff is 0.3% nickel. And note the broad lobe of the mineralization to the east, and the tapering of the mineralization as we move to the west. An Xcite survey was flown in 2016, 100 meter space lines, and here we see some of the EM response with the deposit overlaid on the conductive anomaly. So just note the sharp contrast and conductivity between the background material and the eastern lobe of the deposit, and the diminishing conductivity associated with the shrinking of the deposit to the west. An AMT survey was conducted over the deposit previously, so the decreased conductivity to the west was anticipated. This slide shows some profile data. These three lines are contained, or segments of lines are contained within the black rectangle in the grid. We have a power line moving just to the south of the deposit on these three lines, and you can see the response of the DBT data. This is the Z component of both the power line and the deposit, which is about 1 kilometer away. So these are from channels 18 to 49, and that works out to about 170 microseconds to 12.5 milliseconds. This is a north-looking or north-facing section view of the deposit in reddish brown, and a conductivity depth image that was computed based on the Xcite data. The CDI is cut off at 140 millisiemens per meter, and it has an excellent lateral association with the deposit, but based on the limitations of depth imaging, some of the weaker or the smaller responses weren't located properly at the proper depth. But we see the large broad response associated with the broad lobe of the deposit. This is the same information from a different view, looking south-southwest. So we see the deposit in sort of the rusty red color, the conductivity depth image of the Xcite data, again cut off at 140 millisiemens per meter in pink. And this image includes a recovered 2.2 meter ISO surface from the AMT inversion. So in general, we see a broad correlation, or a pretty good correlation with the broad end of the deposit and the associated geophysical imaging. All right, for the second case study, we stay in Botswana, but this time on the west side of the country, in the Kalahari copper belt, for a copper-silver target. This is from Sandfire Resources. This is their A4 mineral resource at the Matheo copper mine in Botswana. Sandfire's board approved the commercial development of Matheo copper mine in December 2022 around the T3 deposit. The T3 is highlighted here in the box to the right at 5.3 million tons at 0.9% copper and 12.7 grams per ton of silver. So the immediate and most advanced expansion opportunity for the expanded 5.2 million ton per annum Matheo production hub is the A4 deposit, which is located 8 kilometers west of T3. Here you see A4 within the box just to the west of T3. And A4 has 6.5 million tons at 1.5% copper and 24 grams a ton of silver. So this is a geologic section, but first pay attention to the bottom right corner of the image that shows the AB line over a dome structure. And the dome structure is sort of what was of interest to Sandfire. So you see the AB line here, and in the long section we see the AB reference. So we're looking roughly north-northeast. So this shows 2 thrust zones that are associated with the mineralization, along with drill holes and assay results. And the step line outline is a pit, a plant pit. So the copper-silver mineralization is developed along shear zones, and extensional veins are interpreted to be related to thrust movement along the shear zones. The main mineralization is chalcopyrite bornite. So this is all from a press release. So a quote from that release says, "The objective of the AEM survey is to identify new targets within large, previously unexplored areas of Sandfire's extensive license holdings, and further enhance the regional geologic and structural understanding of the Kalahari copper belt. A previous AEM survey led to the discovery of A4 in 2018, figure 4, which I'll show you on the next slide. AEM data, which is processed and interpreted to a high technical standard, has proven to be a breakthrough in defining many drilling targets in the T3 expansion area. And Sandfire is optimistic that the current survey will generate new targets." So this is a layered earth inversion section based on the Xcite data. And as I mentioned previously, the Sandfire is interested in the dome structure and the structures within it that are conducive to hosting mineralization. And here you see the layered earth inversion. which is modeled down to about 600 meters depth, actually quite nicely mapped out the rim of the dome structure itself, which is interesting to see. And then, of course, in the center, you see the plant pit along with drill holes and assays. All right, that's it for case histories. This next section is going to be on system comparisons, and this is just an objective comparison of airborne platforms. Certainly not going to stand here and say that one system is better than the other. So we must note that AEM is a controlled source method. Different transmitter waveforms, amplitudes, and receiver gates, pulse widths will all result in different anomaly responses. So just to quickly illustrate that, we've used a 20 Siemens plate that was modeled in Maxwell, and we've just modeled it with two different turnoff times. Xcite's 350 microsecond in red, and a slower turnoff time of 1 millisecond in black. And what we see is because of the quicker turnoff time, we're measuring closer to the actual turnoff event and measuring higher amplitudes. So that's just one example of how different waveforms affect measured data. So in 2021, at the Australian Exploration Geoscience Conference, Geoscience Australia published a study called Datasets and Inversion Result Comparisons from the Menendee Airborne Electromagnetic Calibration Range. So the Menendee calibration range, or AEM calibration range, it's not really a mineral exploration target. It's a region that is host to a variety of conductivities in the sediments in the area. So Geoscience Australia's purpose was to compare systems based on inversion results, as this would be more objective than comparing raw data. So they used the approach of comparing 1D inversion results using borehole information as control, and also using the same inversion parameters for each data set as best as they possibly could. So this area also has a tremendous amount of ancillary data, including LiDAR topography, borehole information. So the results, including the Xcite system, were published in 2021, and two Xcite surveys were completed for Geoscience Australia in 2020 and 2021. So the results will be shown on the next two slides. But first, the image to the right shows the two test lines that were flown. We have line 10,000, the blue line, to the north, and line 20,000 to the south. So this is line 20,000, the southern line, and well, 5 systems were included in this study. One system was flown at different speeds. But the point being, there are subtle nuances from each system, noise at different places for different reasons, but overall, there is a general agreement in the recovered conductivity from each system. And from line 10,000, just further to the north, we see general agreement from all the systems, general agreement from the borehole logs, and Geoscience Australia's conclusion from the study is, quote, "We have presented our motivation for establishing the Menendee AEM calibration range for assessing and comparing AEM systems. The requirements for flying the range have been outlined, should other service providers wish to fly the range. Our initial analysis using deterministic inversion comparisons shows that all systems resolve the same gross structure over both calibration lines. The inversions also show there is a broad scale agreement with downhole conductivity logs indicating reasonable calibration overall." So to summarize, AEM is effective at mapping contrasts in subsurface conductivity due to the presence of ore bodies or lithological variations, and a new cost-effective method of heli-borne TDEM surveying is now available in Canada. Thank you for your time.